Hi, we're going to start our discussion of the energy related to chemical reactions. So the area of studies called thermochemistry. Okay, thermochemistry. So we're going to talk about the basics of energy, what are energy terms that we need to understand, the idea of calorimetry, which is a way to measure energy changes during a chemical reaction. We're going to look at a thermodynamic function called enthalpy, and then we're going to look at how you can use thermochemistry to understand the energy stored in bonds. And that's really an important concept when we think about things like fossil fuels and the idea that something like methane, which has carbon-hydrogen bonds, stores energy. And we'll think about why that's true at the end of this chapter. So this is just a picture. You start a combustion reaction. So you can start your wood fire, for example, with a match. And a match is just something that increases the rate at which the reaction takes place so that the reaction can start. And then it continues on its own because it's a spontaneous reaction. So we need to know the terms for energy. We need to distinguish types of energy. There are really only two. There's the energy, potential energy and kinetic energy. And then we need to think about the properties of heat, thermal energy, and temperature. We need to think about heat capacity, which there's one called specific heat capacity and one heat capacity. They're really the same concept. And then we want to look at some calculations that allow us to use heat capacities in order to figure out how much heat was exchanged during a reaction. So chemical changes and their accompanying changes in energy are important parts of our everyday world. And I think you probably already understand that your entire body essentially uses the chemical reactions in your food in order to give you energy, to build molecules, to make you move. And we burn fossil fuels all the time, things like gasoline, natural gas, and coal. They're all fossil fuels that are storing energy from ancient solar energy, and then we're releasing that energy in reactions mostly to make CO2 because those bonds are a lot stronger. So there's a release in energy in that process. And then we're going to think about how we use or how thermochemistry is important when we think about making products from raw materials. So oftentimes in order to make, for example, aluminum oxide into aluminum, you have to input energy. So a lot of our raw materials are very energy intensive to make into useful products. So thermochemistry is the study of the heat absorbed or released during chemical and physical changes. So we'll be looking at the chemical reactions, but there won't be what we're interested in. We're really interested in how much heat's given off, usually in those reactions. Sometimes how much is absorbed, we'll see in things like chemical ice packs. These are just pictures reminding us that our food is really just a chemical system that we can use in order to release the energy stored in those bonds in order to build our proteins or to make our brains work. All of the different processes that our bodies do use those energies. The long lines on the highway remind you how much fossil fuel we tend to burn. And the last picture is converting iron oxide into iron in the process, which takes a lot of energy. So energy is the capacity to supply heat or to do work. So those are the two forms of moving energy that are important. There are two main types of energy. I already mentioned this: potential energy, which is the energy an object has because of its relative position. And composition and condition are also really position. So when we think about position, potential energy in reference to position that you're most familiar with, it's probably gravitational potential energy. So if you lift something up and release it, it's going to fall back down because it's in a potential energy field based on gravity. When you think about the composition of a molecule, it's really also because the atoms are in a potential energy field of where the electrons are relative to the nuclei of each species. And so composition is really the same thing. It has a different potential field. That's the Coulomb field. which we'll look at some a little bit, but you want to think that the energy stored in a molecule really is stored in a molecule because of the potential energy of how the electrons and protons are in a field relative to each other. Kinetic energy is always the same. It's always the energy an object possesses because of its motion. So kinetic energy is always 1/2 mass times velocity squared. So it's proportional to the velocity of a particle. This just shows you that if you on the right just lift water up against gravity, it has potential energy. But on the left, it's not until that water actually falls that you can release that potential energy in the form of kinetic energy. So conservation of energy during a chemical or physical change, energy can be neither created nor destroyed, although its form can change. So it can change from potential to kinetic in this case. And when we think about moving energy, which the two ways to move energy are heat and work, you can start out moving energy as heat, for example, when you burn the molecules of gasoline, but then you can take some of that energy and move it in the form of work to move your car. So thermal energy is a type of kinetic energy associated with the random motion of atoms and molecules. So if you think about a sample of water, if you heat it up on your stove, it's going to have more kinetic energy in the molecules. They're going to be moving around faster relative to each other. And so that's how you store thermal energy. And temperature is just a quantitative measure of that thermal energy, of how hot or cold something is. So if molecules are moving fast, they have high thermal energy and you call it hot. And if molecules are moving slow, then you call it cold. They have low thermal energy. This is just a picture to represent that when we think of something as hot, it's because the molecules and atoms in that system have lots of kinetic energy. There's lots of movement. So if you were to stick your hand in that liquid, that kinetic energy could be transferred to your hand, and that's the sensation of hot. This just gives you ideas of how you can measure temperature. When we use a thermometer, such as this one on the left, excuse me. This liquid expands as the temperature goes up, and so it fills more of that column, and you'll be able to see how much more by this very carefully calibrated thermometer. So we're going to do a lab where you look at the density of water, which also means that the volume goes up as the density goes down. So we can also use water in a similar way to using alcohol or mercury. Also shows you on the right that metals have different expansion coefficients. And so you can make this spring either compress tighter or expand by having two strips of metal with different expansion coefficients. So heat, which we give the symbol Q, is the transfer of thermal energy between two bodies at different temperatures. Heat flow, which is kind of redundant because heat is by definition a flow of energy, but it increases the thermal energy of one body and decreases the thermal energy of another. So if you set your hot water and you put a cold rock in that water, the energy is going to move from the hot water into the cold rock, and that thermal energy will then be different in each of those substances. So when two substances are placed in contact, thermal energy will always flow from hot to cold. That's the second law of thermodynamics, which we're not going to talk about in this class, but if you take more physics or take Chem 108, you'll talk a lot about why things change in the way they do. Why is it that you have to use an air conditioner to move energy from a cold source to a hot source and to cool off your house? So those are all things that would involve the second law of thermodynamics. So heat flow will continue until both substances are at the same temperature. So to the point where you have thermal equilibrium. And this is just a picture of that, hot and cold. And when you put them in contact, the energy is going to move until they're both at the same temperature, which means their thermal energies are the same. So we use lots of terminology in this chapter that we have to understand, So matter undergoing chemical reactions and physical changes can release or absorb energy. So sometimes you have to put energy in to make a reaction happen, and sometimes you get energy out. A change that releases heat is called an exothermic process, and a change that absorbs heat is called an endothermal process. So those are just words we have to get used to. This is two situations. On the left, it's an exothermic process. So this torch of being where you're burning acetylene and oxygen is getting very hot, and it's allowing you to melt metal in order to seal the break in this railroad line. On the right-hand side, this is another kind of reaction. And so the left-hand side is exothermic. On the right-hand side, if you've ever used an instant cold pack, you mix together usually ammonium nitrate and water. So they're in there, but you have to break the container that has the water in it. And when you do that, the process of dissolving the ammonium nitrate pulls energy out of the water and cools it down. And so it can be used as an ice pack. So historically, energy was measured in the units of calories. And a calorie is the amount of energy required to raise 1 gram of water by 1 degree Celsius. So that's the definition of a calorie. And we talk about food calories, for example, that would be labels on the food that you buy. Those are capital C calories, and they're actually kilocalories. So 1,000 calories is a capital C calorie. So when we talk about heat, the SI unit of heat, work, and energy is the joule. So a joule is defined as the amount of energy used when a force of 1 Newton moves an object 1 meter. So that's thinking about work, where you have to apply a force in order to move an object. It's just named after a physicist, James Joule, and a calorie is 1.184 joules. We'll mostly work in joules, but if we happen to do something in calories, you'll have that conversion factor. So a heat capacity, by knowing the heat capacity of something, then we're going to be able to measure the heat that flowed in or out of that system. So the heat capacity, usually given a capital C, not to be confused with capital C for kilocalories. So the heat capacity of a body of matter is the quantity of heat that's absorbed or released when it experiences a temperature change. So it's going to have units of heat over delta T. So heat capacity is an extensive property, which means it depends on how much you have. So for example, the heat capacity of a large pan is going to be greater than the heat capacity of a small pan, even if they're made out of the same material, which makes sense. So the specific heat capacity allows us to make more sense out of that. So to take into account that a different quantity is going to have a different heat capacity. So the specific heat capacity of a substance, commonly called its just specific heat, is the quantity of heat required to raise the temperature of 1 gram of that substance. So now if you put that 1 gram into this heat capacity definition, now it becomes an intensive property. It's going to be the same for all iron because you've taken into account that you're only talking about 1 gram. So specific heat capacities in intensive property only depends on the identity of the substance, not the amount. So for example, the specific heat capacity of a large and small cast iron pan are identical because you've divided each of those heat capacities by the mass. So when you go to a table, if you want the specific heat capacity or the heat capacity, it's almost always going to be given in per gram or sometimes per mole. That would be just a heat capacity. But you're not just going to have a heat capacity for some random quantity in a table. This is just visualizing those two pans and how their heat capacities are different for the whole pan, even if they're made out of the same iron. And this is just a table giving you some heat capacities. So just for reference, water has a really high heat capacity. So that's why, for example, you use water in your radiator in your car, because it can take in a lot of heat from your engine and cool it off, and its temperature won't go up that much, which means you won't have your water boiling or something. So water is commonly used to cool things because it has such a high heat capacity. So calculating heat. So if you know the heat capacity of a substance, then you can measure how much the temperature of that substance changes in order to determine how much heat came in or out of the system. So the amount of heat Q entering or leaving a substance can be calculated with this equation. So heat's going to equal the heat capacity times the mass times delta T. And so delta T is just going to be where does the temperature end up minus where does the temperature start. So if a substance gains thermal energy, T final is greater than T initial, and the value of Q is positive. But you could also have a situation where you take heat out of a system and then the final temperature is lower, and then the value of Q is negative. So this is just an example. We have a flask with some water and we heat it. Then the temperature increases from 21 to 85. How much heat did you absorb? So the specific heat of water is 4.184. So that goes in for C, and that's in units of joules per gram degrees Celsius. So that degrees Celsius is also in the denominator. They should make that more clear. And so then if you multiply it by the mass, then you'd have joules per degree Celsius. And then if you multiply it by the temperature difference, you'll end up with just Q, just the amount of heat. So the amount of heat that would have been needed to do that temperature change for that quantity of water is 2.1 times 10 to the 5 joules. And this is just a picture and a little discussion in your textbook about how a thermal electric plant works. So if you can boil water, then it becomes steam. And in that transition, now you can use that change in pressure to run a generator. And all a generator is it's something that goes around. And if you have a magnet that you turn, you create an electric flow, a charge flow. And so that's electricity. So this shows you that you can use solar panels and concentrate the heat from the sun to boil water. But we have many, many power plants that use nuclear energy that heats the water to boil it, or coal or natural gas. And these are just some pictures of these, the solar thermal plants and how large they can be. And the fact that all they're doing is concentrating the sun's energy to boil water, to turn a turbine, which turns a generator, and then the generator, there's a magnet. And as that magnet turns, that creates electric flow. So in order to measure Q, or to get this information we needed for this problem, we use something called calorimetry. So we're going to look at that technique, that method for measuring the heat transfer in a reaction. So calorimetry is used to measure the amount of heat transferred to or from a substance. The heat is exchanged with a calibrated object, a calorimeter, and the change in temperature of the measuring part of the calorimeter is converted into the amount of heat. So the substance or substances undergoing the chemical physical change will be our system. The surroundings will be everything other than that, all the matter, including the components of the measurement apparatus that serve to either provide heat to the system or absorb heat from the system. So in a second, this will be really clear. So a calorimeter is a device used to measure the amount of heat. Many processes measured in calorimeter will occur in a solution. So if the reaction is exothermic, the heat produced by the reaction is absorbed by the solution. If the reaction is endothermic taking place in that solution, the heat's going to be pulled out of the solution to go into the reaction. So this is just a picture of what a calorimeter is. So what a calorimeter really is just an insulated. So you could think of like a thermos bottle as being a calorimeter. And if you have your reaction taking place inside that thermos bottle, then the reaction, if you look on the far left, if it gives off heat, then the solution is going to absorb that heat. And that's an exothermic process. And the temperature of the solution or the surroundings will go up. But if it's an endothermic process, in the process of the system, whatever reaction you're studying happening, it has to pull heat out of the surroundings, the solution, and then that means the solution's temperature is going to go down. So the calorimeter must be well insulated so that when you look at this, you can say that all of the heat that the system produced or took out of the surroundings is equal to what the surroundings lost or gained, so that you don't think of some heat maybe coming out of this gray box and going someplace where you wouldn't be able to measure its impact. So it has to be well insulated. To obtain accurate results, all the heat must take place, all heat exchange must take place only between the system and surroundings. Otherwise, you wouldn't be able to measure it. So something like a coffee cup, one of those styrofoam coffee cups, or an insulated container is often used as a calorimeter in Gen Chem labs. Commercial calorimeters usually are better designed and a little better insulated. So this just would show you a coffee cup calorimeter. You stack 2 coffee cups together, put on a lid, and now everything that's happening is happening inside. And so you'll be able to see if a reaction takes place, whether or not the solution's temperature goes up or down and by how much, and then you'll be able to measure what the Q was. So this is just a picture of a more expensive calorimeter, which you might use if you were in industry really wanting to know, for example, the Q of a reaction to more digits to be more accurate. You might not use a coffee cup, but you may use a more precise instrument. So if you consider a hot piece of metal and some cool water, if the metal is placed in the water in a coffee cup calorimeter or any calorimeter, heat will transfer from the metal to the water. The temperature of the metal will decrease, temperature of water will increase until they're equal to each other. And when that's true, then you know that you can measure how much heat flowed into or out of each. So since this is done in a calorimeter, the heat exchange is only between the metal and the water. So the net change in heat is 0 for the whole world. But rearranging shows that the heat gained by the metal is equal to the heat lost by the water. And so the heat of both substances is equal in magnitude, but opposite in sign. And this is just a picture of that, looking at putting the metal in there and waiting for it to both be purple, so they're in thermal equilibrium on the right-hand side. So we have a 360 gram piece of rebar, which is just steel. We drop it into some water, 425 mils at 25 degrees. The final temperature of the water was measured to be 42. We want to know the initial temperature of the piece of iron that you put in there. So we're going to assume the specific heat of steel is approximately the same as that for iron, and that all the heat transfers between the rebar and the water, and there's none lost to the environment. So the temperature of the water increases from 24 to 42. So heat's absorbed. That heat came from the piece of rebar, which must have been at some higher temperature. So assuming that all the heat transfer was between the rebar and the water with no loss to the environment, then we can say that the rebar's heat equals the negative of the water heat. And we have equations for those. We just need to know the quantity of rebar, the heat capacity of rebar, the quantity of water, the heat capacity of water, and we should be able to figure out what that initial temperature was. So if we put in all of those numbers, so the heat capacity for the rebar, 0.449, which you'd get out of a table, you have 360 grams of that, starts out at 42.7, or it ends up at 42.7. The water specific heat is 4.184, so the left-hand side equals the negative of the right-hand side. We had 425 grams of water because we can assume the density of water is about 1 gram per milliliter. So if you have 425 milliliters, you have 425 grams. And the water started out at 24 and went to 42.7. So we should be able to figure out by just rearranging this equation that the original temperature of the rebar was 248 degrees Celsius. So when we use calorimetry to determine the heat involved in a chemical reaction, the same principles we've been discussing apply. So it can be just heat moving from one substance to another, but it could also be, rather than putting a chunk of metal in, you're putting something into that system that chemically reacts. And then you can also look at the temperature change and decide whether or not that reaction gave off heat or absorbed heat. So because energy is neither created nor destroyed during a chemical reaction, the heat produced or consumed by reaction, the system, Q reaction, plus the heat absorbed or lost by the solution, the surroundings, must add up to 0. So it's exactly the same as our metal in water, but now it's a chemical reaction. So the Q of the reaction plus the Q of the solution has to equal 0. So they have to be equal to the negative of each other. And so if we have 50 mils of acid and we react it with 50 mils of base, and they're both at the same concentration and both at the same temperature, we put them in a calorimeter and wait for the reaction to take place. The temperature in the end is 28.9. We want to know the approximate heat produced by that reaction. So first we need to know the chemical reaction. So we think back to our discussion of acid-base chemistry, and the reaction of HCl with sodium hydroxide makes NaCl and water. And so to visualize what's going on, imagine that you could combine the two solutions so quickly that no reaction took place while they were mixed. Then after mixing, the reaction takes place. And at that instant, you have 100 mils of a mixture of acid and base, and the acid and base then react until the solution temperature reaches 28.9. The heat given off by the reaction is equal to that taken up by the solution. So we can figure out how much was taken up by the solution, because it will be the heat capacity of the solution times the mass of the solution times how much its temperature changed. And so our solution, if it's a dilute solution in water, we can assume it has the same heat capacity as water, so 4.184 joules per gram degree Celsius. And once again, the gram and the degree Celsius are in the denominator. We're going to multiply that by the mass of our whole solution. So our solution was 100 milliliters. And if it's dilute, we can assume it has approximately the same density as water. So we will say 100 milliliters is 100 grams. And we measured the temperature change. So it started out at 22 and it went to 28.9. And so the Q for the solution is 2.9 times 10 to the third joules. And that means that the reaction has the opposite Q. So that means that the reaction of HCl with sodium hydroxide is exothermic. It gives off heat. So it gives off the same amount of heat that would have been absorbed by that solution. So the negative sign is what tells us it's exothermic, and the reaction produces, it gives off 2.9 kilojoules of heat. So you can use reactions like that to create, just like you had the cold pack, you can have a heat pack. So you can put chemicals into a heat pack where if you break the barrier that's separating maybe the water from whatever you're going to put in there, you can have the reaction take place. And if it's an exothermic reaction, then that heat bag is going to heat up, and you could use it just like you could use an ice pack, only this case it would be a warm pack. So we already talked about a cold pack. This is just looking at a bomb calorimeter, which we have one in the chemistry department. It's a similar kind of idea, except the calorimeter has to be sealed because it's used to measure the Q for reactions that are combustion reactions where you're producing gases. And so you have to keep that all sealed in there. And so often the pressure goes up. So you have to have what's called a bomb, something that's very resistant to expansion and won't break as pressure changes. So its volume stays constant, and you can burn something in there, and then the calorimeter's temperature change can tell you how much heat was released in that combustion process. This is just talking about the nutritional facts. So when you talk about calories on a food product, it's the same idea. Now that food is eaten and your body carries out the chemical reactions to give you the energy from those chemical reactions. So I am going to take a break now. We're about halfway through, and we will come back and continue talking about thermochemistry in a second lecture.